Hello and welcome to the TI Precision Labs module discussing power supply noise in ADC systems. So far in the ADC noise modules, we focused on noise contributed by signal chain components that could either be external to or integrated into the ADC. However, power supplies can also contribute noise. This module introduces the types and sources of power supply noise, how to measure and quantify power supply noise rejection, and discusses how noise on each ADC supply impacts the system performance. This module also assumes that the power supplies are fixed. In other words, we won't discuss power supply design techniques that could change the power supply noise contribution. Instead, we'll focus on how this noise affects the ADC output. To begin, let's define power supply noise. For any analog signal chain, power ultimately comes from one of two sources, batteries or AC line voltage. Examples of these power sources are shown on the left. Both power source options are often followed by some form of power supply conditioning circuitry that regulates power from the rest of the system. Shown in the middle of this slide are some examples of power conditioning circuits, including an LDO on the top and a DC-DC converter on the bottom. The supply source, as well as the active and passive conditioning components, contribute some level of noise, which manifests itself in the power supply output as a variation from the expected voltage. This variation could appear as a steady DC shift in the output or as an AC signal at some frequency and amplitude riding on top of the output. LDOs primarily contribute thermal noise, like that associated with all electrical components. Switching devices such as DC-DC converters can add large current transients on top of thermal noise. Current transients generally consist of both a lower frequency ripple, typically less than 1 MHz, as well as higher frequency spikes greater than 100 MHz, centered on the nominal output voltage. The oscilloscope plot on the right shows an example of all types of power supply noise coming from a switched mode power supply, including switching ripple, transient spikes, and thermal noise. In addition to power supply conditioning components, AC noise can originate from other switching components that use the same supply, such as clocks and clock buffers, as well as from ambient lighting or other environmental elements. Ultimately, the ADC power supplies will likely have some combination of both thermal and switching noise regardless of which power source is used. However, since power supply noise is external to the ADC, semiconductor manufacturers can only specify how effective an ADC is at rejecting this noise. This specification is called power supply rejection ratio, or PSRR. The equation at the top of this slide identifies how PSRR is calculated in an ADC datasheet. PSRR is the change in the ADC output, delta V out, relative to the change in the ADC power supply, delta V supply, and is commonly given in decibels. Note that the absolute value is conventionally used to describe PSRR, since the negative sign is implied. As with most ADC specifications, PSRR can be defined in the electrical characteristics tables in the typical plots or both. The plot on the left shows the ADS127 L01 PSRR across a frequency range of 0 kHz to 500 kHz. Note that all three supplies are provided in the plot where AVDD is the analog supply, DVDD is a digital supply, and LVDD is the ADC modulator supply voltage. Comparatively, the tables on the right represent PSRR specifications found in the electrical characteristics of an ADC datasheet. The top table shows the ADS1261 PSRR specifications at DC, while the bottom table shows the ADS127 L01 PSRR specifications at 60 Hz. Importantly, the tables on the right show that PSRR can be measured in two different ways, PSRR DC and PSRR AC. The PSRR measurement method used in an ADC datasheet depends on the types of signals the ADC will measure. These two specifications are discussed in more detail on the next few slides. PSRR DC describes how much the ADC output changes due to a DC shift in the power supply. The measurement setup for PSRR DC is shown on the left. To measure PSRR DC, short the ADC inputs together. Bias them to a common mode voltage VCM that is typically near mid-supply, and measure the offset voltage at the ADC output. Then, the supply voltage is shifted by some small value to see how much the ADC offset voltage changes. Using the PSRR equation on the bottom left yields the specified value provided in the datasheet. For this example, let's assume that the analog supply experiences a DC shift of plus or minus 100 millivolts. In the time domain, the AVDD voltage resembles a plot on the top right, where the minimum and maximum offsets are shown in blue centered on the nominal supply voltage, V supply. Given this 100 millivolt offset on AVDD, we can use the equation in the bottom left and the ADS1261 typical PSRR in the top right to determine that a 100 millivolt change in AVDD should produce a 1 microvolt change in offset voltage at the ADC output, which is shown on the bottom right in red. Note that the output offset voltage swing is centered on the ADS1261's nominal offset voltage represented by the green dotted line. The measurement setup for PSRR-AC is very similar to PSRR-DC, where the ADC inputs are shorted together and then biased to a mid-supply common mode voltage. However, instead of introducing a DC offset to the supply, measure PSRR-AC using a sinusoidal AC signal riding on top of the nominal DC supply as shown in the blue plot on the right. This sinusoidal AC signal mimics noise at a particular frequency. For example, 60 Hz is used for the ADS127L01 PSRR measurement, as shown in the table in the top right. In a real system, however, power supply noise may not be purely sinusoidal. In this case, ensure that the ADC and other components can also reject harmonics of the fundamental noise frequency. To calculate PSRR-AC in the time domain, use the PSRR equation shown in the bottom left. Using the 100 millivolt amplitude as V supply and the ADS127L01 AVDD PSRR from the table. The expected variation in the ADC output is a 3.2 microvolt signal oscillating at 60 Hz. This is shown in the bottom right in red and is centered on the nominal ADC offset voltage represented by the green dotted line. You can also calculate PSRR-AC in the frequency domain by converting the 100 millivolt supply ripple into decibels using the ADC reference voltage. Assuming a 2.5 volt reference voltage, 100 millivolts equates to negative 28 dBFS, or decibels relative to full scale. This is shown in the plot on the right in blue. The PSRR-AC in this case is a difference in decibels between the supply ripple amplitude and the tone measured in the frequency spectrum that appears at the supply ripple frequency of 60 Hz. This is shown in the plot on the right in red and results in an error signal amplitude reduction of 90 dB at 60 Hz. While our analysis has focused exclusively on AVDD thus far, ADCs have other supply voltages that can introduce noise. This begs the question: which supply is most critical to minimize noise? To answer this question, let's review the plot on the right that was introduced previously during the discussion about PSRR datasheet specifications. This graph plots the PSRR versus frequency for the ADS127L01, a 24-bit delta sigma ADC with a wide bandwidth digital filter that can sample up to 512 kilosamples per second. Importantly, the ADS127L01 also has three distinct supply voltages. AVDD is analog supply in black, DVDD is digital supply in gray, and LVDD is ADC modulator supply voltage in red. From the plot, it is clear that the modulator supply, LVDD, has the lowest PSRR, and therefore the highest susceptibility to power supply noise. Let's explore this concept in more detail on the next slide. To test which power supply is most critical with respect to power supply noise, follow the test procedure outlined on the top left. First, perform a baseline PSRR measurement on the ADS127L01 EVM using clean supplies. Use the same PSRR AC test setup as described throughout this presentation. Next, apply a noise signal on top of the nominal supply voltage. In each case, this noise signal is applied to only one supply at a time, while the other two supplies are kept noise-free. Finally, measure the ADC output, assuming shorted inputs, then calculate the resulting noise. The test parameters used in this experiment are shown in the table on the left. The noise signal is a 100 mV, 1 kHz sine wave that is centered on the nominal supply voltage. The nominal supply voltages are given as 3 volts for AVDD, 1.8 volts for DVDD, and 1.825 volts for LVDD. On the right are histograms reporting the results of each test. The baseline test is shown in green and has an input referred noise of 3.71 microvolts RMS. The test with noise on AVDD is shown in black and has an input referred noise of 3.81 microvolts RMS. The test with noise on DVDD is shown in gray and has an input referred noise of 4.9 microvolts RMS. The test with noise on LVDD is shown in red and has an input referred noise of 9.37 microvolts RMS. As predicted, LVDD is the most susceptible to coupling noise into the ADC output because it has the lowest PSRR of the three supplies. LVDD is most sensitive to noise because it directly powers a delta sigma modulator, which in turn directly controls the analog to digital conversion process. Comparatively, AVDD powers the remaining analog circuitry, including generating the main bias current, but this has less of a direct impact on the conversion result. DVDD powers the ADC digital core and has the least impact on the conversion result because the modulator output is already in binary form when it reaches the digital decimation filter. Ultimately, for devices that require multiple supplies, prioritize using a low noise, high PSRR regulator for the supply that directly powers a delta sigma modulator, which is typically AVDD. If the power supply noise is still too high, it might be necessary to try additional noise mitigation techniques. These techniques are described in a subsequent Precision Labs module. That concludes this video. Thank you for watching. Please try the quiz to check your understanding of this video's content. Question 1. The PSRR of a particular ADC is 120 decibels. How much power supply noise appears in the output if the power supply noise amplitude is 100 millivolts? The correct answer is D, 0.1 microvolts. Question 2. For the PSRR curve below, would the power supply noise rejection be better at 50 kHz or 350 kHz? The correct answer is B, 350 kHz.